I'll give you a little silence.
But there's another use case for the bell.
All right, well, welcome back. I'm going to have Yihan Sun talking about scalable parallel algorithms.
Okay, good. Okay, thank you very much, and welcome to my talk. So as you can see, the official title of my talk is Scalable Parallel Algorithm. Is kind of a big and ambitious title of the talk. And the actual title is even more ambitious, which is Theory and Practice of Scalable Parallel Algorithm. I'll actually not able to talk about such a big topic in just 30 minutes. So the actual content of this talk will be our recent Sigma paper on K-core decomposition as a case study. And I'll introduce some, we believe, very interesting techniques in this case related to both theory and practice about scalable parallel algorithms. Okay, and in many of my talk about theory and practice of parallel, So one thing I feel especially interesting about this work is that actually we didn't improve anything like worst case bound in this paper, but we believe there are many interesting theoretical content behind it, but just need some more exploration. So I feel probably this is a good topic to talk about here. Okay, so anyway, so when I talk about theory and practice of parallel algorithms in many of my talk, I show a joke like this at the beginning of the talk. And people usually really like this because I guess people like dogs. I even have a video version of that. So it's like this. Okay, so what happened is that I saw this video online. This was pretty cute. I was laughing until I saw the title of this video, like this. So I couldn't laugh anymore. But yeah, that's the case. And I guess you all got the point. Like the dog's eye are like the threads. And when you code more threads or more docs, they're cute, but they do not always mean better performance, but almost always mean more troubles. So the problem here is that your threads may not always collaborate with each other in the way you want. If you want them to collaborate, you probably need to pay something to synchronize them, to schedule them. That can be a high cost, and in many cases, they're kind of hidden your theoretical analysis. And on the other hand, you can let them just work on the task asynchronously. But if you're not careful enough, they may also cause troubles. They may be slower because they contend with each other, or you may even have correctness issues. So these are not new statements. We've seen many talks addressing one or two of these two things here. And one thing we feel interesting about our K-core work is that actually exactly these are the two things we need to address when we engineer the algorithm. Okay, and actually there are many more complications for parallel programming. I'll just focus on this two today, and they coexist in one work. Probably need to deal with multiple of them, and altogether, maybe you implement the parallel code, the parallel algorithm. It can be slower than the sequential code. That's usually something you may need to pay extra effort to deal with. Okay, so since we'll talk about theory, I'll first quickly set up the background about the model. We assume shared memory, binary fork join. And when analyze the algorithm, I guess many of you here are familiar with the work span model. Work is the total number of operations, that's the sequential time, and span or depth is the longest dependence chain, that's the best parallel time you can get. We assume there's work stealing scheduler, so we just design an algorithm based on fork join, parallel fork, and things like that. And importantly, we care about work efficiency. It means that your work of your parallel algorithm is asymptotically the same as the best sequential algorithm. It means that even though your algorithm has a bad span or very little parallelism, or when you only have a little, like a few number of cores, you still have your parallel code perform as well as a sequential algorithm, ideally. Okay, so That's it. And in many, this is standard definition. In many parts of this talk, will raise the question like, is this sufficient? What else do we need to understand to make a running time estimation more accurate in practice? Okay, so let's talk about the main topic of this talk, which is about K-core decomposition. So this is a classic graph processing problem. So K-core of a graph is let me try. Oh, no. How can I? Okay. K-core of a graph means the largest induced subgraph where every vertex has a degree of at least k. So here is an example of a graph, and it's 1 core, 2 core, 3 core. So usually what we want as an output of the K-core algorithm is a coreness of each vertex, which is largest k such that it appears in the K-core of the graph. So what you need, the output will be something like this. So it indicates how central a vertex is in your graph. Okay, so this is a classic problem, very well studied and widely used in a lot of applications. And sequentially, we have a standard solution that has linear work. So in parallel, we also want to match that. Okay, so for both sequential and parallel setting, finding K-core is based on a process called peeling algorithm. So the idea is that starting from the entire graph, say it's just a 1 core, and when we move on to 2 core, what we want to do is we just peel all the vertices with degree smaller than 2, so in this case, all the degree 1 vertices. And during this process, after peeling them, the degree of other vertices may be updated, and then we'll expose more 1 degree vertices. In this case, we'll repeat this process until all vertices have degree 2 or more, so that's our 2 core. And we then move on to the next k and repeat this process, so on and so forth, until the graph gets empty. So that's the high-level idea of the algorithm. So in this talk, we'll call the outer loop a round, each dealing with 1k, and inner loop a sub-round, each dealing with like a frontier or something. And if you want to achieve parallelism, you can achieve parallelism here, since you can peel all vertices in parallel. But for sub-round, you have to do that one after the other, the same for the round. Okay, any questions so far?
So it should be just 1 to n, right? You can't have more than n.
Yes, but we have a stop when. Yeah. Okay. So to get efficient solutions, an algorithm needs to answer 2 questions. The first one is how can we identify all vertices with degrees smaller than k. The other is how we update the degrees after peeling. An existing parallel algorithm exactly differ in how they answer these 2 questions. So, for example, if you want to peel in this way, so one of them is, we call it offline peeling, which is proposed in Julian in Leitchman, Julian and Guy's SPA paper. So the idea is that I'll first collect all the degree decrements, okay, and run a histogram or semi-sort-like algorithm. I'll compute the total decrements for each vertices, and then run another parallel for to apply them, actually. So that's the idea. For the second question, they propose a very interesting data structure called bucketing structure. So this helps them to achieve work efficiency in their algorithm. And the other category, we call it online peeling. It's more straightforward. It says, why don't we just use atomic operations so it can be directly applied to, the decrements can be directly applied to them on the fly, so that we call them online. This is we call it online strategy. And for some reason, all of them use a very naive way for the second part, so they have a suboptimal work bound. But as mentioned, these 2 things are kind of orthogonal. Actually, you can combine them in like arbitrary way. Okay, as we can see, the first style is corresponds to a more synchronous way of algorithm design. The other one is more asynchronous. So later we'll see exactly the performance overhead for the first one comes from synchronization, and for online algorithms, it comes more from the contention. So why do we want to study the problem again? Very interestingly, when we start to look at this problem, we find there are many something to explore both in theory and in practice. So in theory, the interesting thing here is that although Julian actually achieved the work efficient algorithm, but that work efficiency highly rely on their data structure, the bucketing structure, and in their code, they actually simplified it a little bit because probably the previous design is not that easy to code. So they have a simplified version, and they hypothesize it to be work inefficient. So when we started to look at the problem, one question we want to answer is whether we can get a work efficient solution, but also simple enough to code and perform well in practice. And in practice, the interesting thing here is that both online and offline strategies have their bad case. They're different. So first to show you some performance numbers, we first tested dense graphs. And in this case, offline strategy, Julian, performed pretty well. But the online strategy can be pretty bad, like 10 times slower than sequential algorithm, which means you shouldn't use parallelism at all in this case. But if you move on to sparse graphs, it's the other way around. The online algorithm perform pretty well, but offline algorithm may be inefficient in this way, so have very little speed up. So as a spoiler, our algorithm can always achieve a better among them. In many cases, in almost all cases, we are also faster. Okay. So let's take a closer look at what's happening here. It's probably not too surprising to know the online strategy is not good on dense graphs because when you have a lot of atomic operations to update the high degree vertex, you may have high contention. For the offline strategy, the problem may be a little bit trickier. The thing here is that assume we have a sparse graph like a grid here. And what peel vertices, the peeling process may have a chaining effect. For example, we'll start with the 4 corners of degree 2 vertices, remove them, we'll expose more of them, and have to do that again. So even though there is only one round in the entire algorithm, there are order of root n sub-rounds. So the problem here is that in between every 2 sub-rounds, you may need to have a global synchronization to have parallel for, so on, to distribute the tasks. So when you have a large number of sub-rounds, this synchronization cost can be significant. On the other hand, since the graph is sparse, you almost always have a very small frontier, so you don't have sufficient parallelism to explore. So the two things are kind of related to each other, but from different angles, both affect the performance of the algorithm on sparse graphs. Okay, so as we can see, existing algorithms either suffer from high contention when it's asynchronous or high synchronization cost when it's synchronous. Okay, so what did we do? In theory, we proved a small thing. Very interestingly, we summarized an algorithmic framework that unifies online-offline peeling that is work efficient, very simple. We proved that you don't need a bucketing structure to make the algorithm work efficient. And also we proved that the implementation in Julian is actually work efficient, different from what they thought. So it's pretty nice side effect we got. And in practice, we proposed several new techniques to optimize the performance. In practice, I'll talk about more details later. So I'll start with our algorithmic framework. It's super simple paper, just 1 page or so. Just I want to quickly mention that. So on top of the general framework, we just add one more very little detail, which is we maintain an active set here, which is all the unpeeled vertices. And whenever you need to peel vertices in a round, you find them in this active set instead of using all vertices. And similarly, when you finish a round, you always try to update the active set to keep it up to date. And for both of the extra step that can be done about a parallel filter, that's linear work in A. So it's not too hard to prove that the total size of A is linear, so that will give you the bound of linear work for your algorithm. And if you're familiar with Julian implementation, this is almost exactly what they did, just without using the bucketing structure. Okay, so that's the algorithmic framework. More interesting part is actually we used some new techniques to make the implementation much faster in practice. And again, these are the two existing methods. In our work, to leave some space for asynchrony, we choose to use online peeling as a base design. So the first thing we need to address is how we get rid of the high contention for large degree vertices. So our high-level idea is very simple. Since we don't want to run so many atomic operations on one variable, why don't we just use like sampling idea? We perform actual fetch and add with just a probability of P. Okay, so now if you have C sampled decrements, it roughly means you have C over P decrements in reality. Okay, that's the full idea, but the problem here is that it's roughly good enough for what we need. So I'll show you an example to see, like, now it's not that much trivial. So assume you're having an algorithm running at k equals to 500, so now you want to get all the vertices at degree 500. However, if you have a vertex in sample mode, maybe starting from a huge degree, but the degree, like 1,000, but the degree has roughly decremented by 450. And in this case, should this vertex be counted? So the problem here is that you must identify the true degree when k hits the corners of V, okay, so that it can be peeled in time. If you miss a vertex, then there will be error for both this vertex and its neighbors and so on. So we don't want to have such error. And the corners of V is different from for each vertex. The value of k is also dynamically changing. You want to know exactly the moment when they meet in the middle. So first of all, we want to take as few samples as possible. And second, when the degree gets close to k, we need it to be accurate. So that's the main design goal of our algorithm here. So our solution is based on a multi-level sampling idea. So starting like when we start, if a vertex has a sufficiently large degree, we turn on sample mode, meaning that we'll just use sampling to estimate its degree. At the beginning of each round, we'll check all the sampled vertices. If it's still safe, it has a degree, with high probability, it has a degree more than a constant over k, more than constant factor over k, then we do nothing, we'll continue. Otherwise, we'll reset the sample parameter to make it more conservative, or quit the sample mode when we decide it is very close to k. And here, this condition can be determined by just using some math. And you can check the error probability based on the current parameters of k, original degree, sample rate, and so on. And you'll need to guarantee this error happen with very low probability. Okay, and you can use union bound to prove the entire algorithm is correct with high probability. You'll see that there still can be an error, but if an error occurs, our algorithm can always detect it, and you can simply restart. In all our experiments, as long as we set the parameters properly, actually we never see such a case of restarting. Okay, so this is a high-level idea. It's probably I'll mentioned like many times, a lot of the techniques in our papers are super simple. This is probably the most complicated part because you need some math. Most of the theoretical analysis in this paper were trying to prove that this is correct or it is correct with high probability. but we were actually it improved the performance and reduced the contention, but we were interested in knowing what happened in the cost bound, since it reduced the running time. Did we improve the cost in some sense? So we proved that what we can prove is that the number of logically concurrent decrements to a vertex V can be reduced from the degree of V to the coordinates of V plus log n. So for a dense graph, this can be very, very significant. Okay, but the very interesting question here is that actually, this kind of reflect the contention, but it's not exactly the definition of contention in most of the previous papers we know of. We find the most close related one is a Popov 17 paper, but it's also very interesting to try to understand is this thing we want for fork join in analyzing contention in a fork join algorithm and so on. The other interesting future work is that the sampling idea is basically just about the proximate counter. There exist many other proximate or concurrent counters in the literature. Maybe they have different goals, but they are very close connection between them. So can they be used for K-core, other peeling algorithm, and many other graph algorithm requires counting like maximal independent set and so on. And also can our idea be used to improve their use cases? What's the actual connection there? So these are some interesting open questions we had in this direction. Okay, so any questions so far? Okay, good. So so far we spent some time solving the lower part here, solving the problem lower part here. But if you think about the framework again, even if you use an online algorithm, if you use a faithful implementation of the framework, you still have to deal with the number of sub-rounds and so on, and you have this problem of synchronization costs and small frontier and insufficient parallelism. So our second technique is exactly trying to deal with that. And probably said this many times, idea is super simple. So what happened here is that we call this a vertical granularity control. We'll see why this is a name later. But the idea is that when we peel a vertex, we always set up a fixed size local queue to buffer the ready vertices directly. So because we use online peeling, we can immediately identify if a neighboring vertex is ready. And then we process them immediately instead of waiting until the next sub-round. So here, again, we start from the 4 corners, and all of them will decrement the degree for their neighbors, and they immediately get a degree of 2. So we'll process them directly. Okay, assume we have a queue size of 4. When they get 4, when they get full, we will push the rest of them to the next sub-round just as usual. So in this case, every vertex process at least 4 more vertices when they peel. As long as there are possible work to do, they always do at least 4 here. Okay, so that's it. This can reduce the number of sub-rounds, and it's kind of load balance, and there's no overflow. So because we use a fixed size queue, and the very interesting side effect is that after that, you may get your frontier grow much larger in the next round. So even though you start with no sufficient parallelism, you may get sufficient parallelism after 1 or 2 rounds of such, we call it local search or something. So you may get sufficient parallelism in 1 or 2 rounds later. But if you run a standard algorithm without such a search, maybe in all the rounds, you never get sufficient parallelism in your frontier. Okay, so again, question.
On the previous slide, so are you sending atomic decrements for the degree updates while processing within a queue? Is that how this works, or
yeah? So Yeah, that's a good point. So because we use atomic operations to update their degree, so whenever it hits the current k, that's a signal that it's ready. So whoever decrement it to k will be responsible for processing. Yeah. Okay. Cool. Any other questions? Okay.
Is there some way of determining what is the right size of this local queue? I mean,
Okay.
any analytical and not empirical?
Okay, that's a very good question. So far what we did is, like a general finding is that as long as you do something in a very large range of the parameter space, the performance is similar, just like regular granularity control. But we think if you like plug in like the actual number of like scheduling overhead or something, you may be able to get some analytical like results about that. I'll actually have a separate slide talk about that. So I'll see if that better answer your question later. Okay, so that's the last part for our technical design. But although this is just 2 slides, but we feel it's even like more interesting in many aspects. The first thing is again, how should we understand improvement in theory? It also apparently improve the performance, but if you consider it doesn't affect the work at all, it improves parallelism, it doesn't improve span, it also increases span. Okay, so it means that you're using more sequential operations to increase parallelism. If you find this statement strange, just go back to consider the regular nature of regular granularity control. It's the same thing. Okay, so previously at previous slides, like, do you like how many of you know granularity control? But Sam just gave a very nice talk this morning, probably set up the background for me. So thank you very much. But in general, just in case you don't know much about that, so the idea about granularity control is very fundamental for parallel programming. So assume you implement an algorithm of reduce, like this is a textbook algorithm. To divide and conquer, you have a base case of get 1, and you can implement this in C++. It will be tens of times slower than a sequential algorithm. Okay, it has optimal work, optimal span, but it can be much slower than sequential algorithm. And it's a very easy fix, which is just to turn the base case size to a threshold. There's yet another way of doing that. You can use Sam's compiler, so you don't have the trouble anymore. But let's focus on like a old style thing, which is you have to manually turn this to get granularity control. Okay, so this is not surprising, but the question is how should we understand this in theory? So we try to study this, look at a lot of papers. We think what we did is very similar to granularity control, but it's a strange way. Like in classic way, you we call it horizontal granularity control. It would be easy to be applied to parallel for or divide and conquer, but in our case, we actually change the computational DAG. We break the synchronization point and put multiple frontiers in one task and run it sequentially. So it's kind of strange compared to classic ones, but it also worked in the same way from the same motivation. Okay, so we then find a paper on something called burden span. It's used in Silk and still in OpenSilk. It says that, okay, if you want to take that into account, you can count each fork join just with a higher weight in your span. So probably you can just take the synchronization cost into consideration. So with help of TB, with the help of TB, we were able to run some experiments on that. I'll show you some interesting results later. And the other one is just, again, related to, we believe this idea is kind of general. We have explored a few graph algorithms that all use the same idea and improve the performance, especially for large diameter graphs. And we are looking for more and to better generalize it, this idea to more applications. Okay, so that's most of the content for the technical part, and I'll move on to experiments. As I promised, I'll show you some interesting results. Okay, so we use 96 core machine, and we use Parallelism as to support fork join parallelism, some primitives. We also used OpenStalk to test burden span, as I mentioned. We tested our algorithm compared to both offline and online algorithms, and we used a very diverse data set, and we even designed some synthetic graphs that simulates the worst case for all these algorithms, including our own algorithm. Okay, so first take a look at the comparison with the baselines. So you have a lot of bars here, so don't worry. So they are just a relative running time to our algorithm. So if you care about our algorithm, that's a red line here. So all the bars are like how much they're slower than us. Okay, so if we look at the subset of dense graphs, as we mentioned, the offline algorithm performs pretty well, and the online algorithm overall has a bad performance on them. But if you go to the sparse graphs, in many cases, the online algorithm can achieve very close to our performance. But on the other hand, the offline algorithm would be more inefficient. But in both cases, our algorithm is always the best or close to the best here. We also tested how much each technique contributes to performance. And here again, you can see a lot of bars, don't worry. We have the red line here as a plain version without any optimization. And the blue bar shows how much improvement you get with VGC. Yellow is how much improvement you get from sampling. So higher is better, blue is with both. Okay, so sampling is kind of special. On most of graphs, it doesn't help because no vertex has high degree enough to trigger it. Only on like about 8 very dense graphs, among them, sampling had improvement, but improvement is usually very significant. For VGC, it almost always improves performance a little bit, but the more sparser a graph is, the improvement is more in this case. Okay, and then we were curious about how burden span really help explain the improvement. So we use OpenStalk to measure that. In general, OpenStalk will report you a number, which is the critical path. The length of critical path, but charge a constant for each fork join. It's empirically set to 15,000 something, so it's really pretty large constant. And we compare all the numbers with Julian. So this baseline here is Julian. We choose it as a baseline because you can trust them did the best engineering effort in a pure offline algorithm. So first of all, we change offline to online. These are the blue bars. We already see some improvement. That's because the computation within each round for online computing is more has less synchronizations. Like in offline version, you need to collect the decrements, run histogram or semi-sort, then apply the operations. So all of them will be some synchronization. And later, when we change it to with VGC, then we have even more speed up. So that actually very accurately, the trend very accurately match the running time. Okay, so I'm a little bit over time. Sorry to Lexman. So this is a summary. So in theory, we came up with an algorithmic framework, unifies online-offline peeling. It's work efficient, very, very simple, very easy to code. And in practice, we have several interesting techniques that actually improve performance, especially addressing both scenario for synchronous and asynchronous setting, how you reduce the overhead. And as I mentioned, there are many, many open questions in this scope that we actually feel that are interesting to explore in the future, especially for the burden span part. I see very little theoretical work on this side. So we're interested in knowing if there's anything we can proof in this case. And where we have a more similar topic, I'll probably just stop here. But if you're interested in both theory and writing fast code, I think we're here to talking to people. If you're interested, just talk to me offline. So that's it. Thank you very much.
So the burden span is good intuition, I think, for the vertical. Like it seems like a good intuition for the vertical granularity control. But there's another thing with which you're tuning here. So when you pick this queue size, you're also now doing more asynchronous synchronization, right? Because you're submitting more kind of atomic decrements out into the ether. So like there's some sort of trade-off happening here, right? So like maybe burden span accounts for the fact that you have fewer synchronizations across the sub-rounds, but you also have kind of implicit synchronizations happening in the memory system of the machine, right? Is that a good intuition? Or?
Yeah, I think that's a good point. So the thing here is that actually we did two things. Both of them kind of need some theory to explain. For the burden span, like for example, when we apply that to other problems, they not necessarily always cause more atomic operations. So the idea in searching, this is a kind of special for K-core that you need to use fetch and add. For many other algorithms, there's no such very heavy contention in this case. So if you view them as independent parts, so you still can use burden span maybe to model something, and probably as Kuba just mentioned, how do you set the queue size in a proper way using like mathematical idea or something? Is probably related to how much like the parameter in your model, like the 15,000 or something. That parameter probably would affect the best queue size. So you may take that into account when you design an algorithm. That's our intuition. We didn't have any progress yet. So that's just a personal feeling about that. Yeah.
Great. Thank you.
Okay, thank you.